Okay, and so here we have Part C, which is, assesses Standard 4 as a written response, free response, however you want to call it. So 66 to 85, again, the 2-point questions are have two question numbers, like 70 and 71. And so we have a vector question to begin with. It says 66 through 69 on the information and vector diagram below and on your knowledge of physics. So let's get started. So it says a hiker starts at point P, walks 2 kilometers east and 1.4 kilometers north. Vectors in the diagram present the two displacements. A 66 using a metric ruler, determine the scale used in the vector diagram. Well, when you're dealing with virtual documents like PDFs and things, you can really make it any scale that you like. So I can tell you what the official scale was for the Regents for this exam, and that based on the official scale, that 2-kilometer vector should be 5 centimeters long. So that if you held up a metric ruler to it, starting at P, going to the tip of P, that 2-kilometer vector, displacement vector, 5 centimeters long. And so the scale, so if a 2-kilometer vector is 5 centimeters long, then how many kilometers is 1 centimeter? So we can set up a ratio and solve for x, and we wind up with 2 over 5, which is 0.4. So 1 centimeter is 0.4 kilometers, and they'll accept anywhere from 0.38 to 0.42 for that answer. Okay, 67. Use a ruler to construct the vector representing the hiker's resultant displacement. So if the hiker is hiking 2 kilometers to the east and then 1.4 kilometers to the north, we start from the starting point P and we draw our resultant vector from P to the stopping point from start to finish, and we include an arrowhead. I do believe you don't get the credit if you don't have an arrowhead. I just pressed a button. How do I get rid of this thing? Close. Good. So, going from start to finish, that's how the resultant goes, and there's the drawn vector. But remember the arrowhead. Very important. Okay, 68 says, determine the magnitude of the hiker's resultant displacement. So you can do that with a ruler, now that we have a scaled vector diagram. If I measure that with a ruler, I get in centimeters. I measure that to be about 6.1 centimeters, and using the scale of 1 centimeter is 0.4 kilometers, I get 2.44 kilometers for the resultant displacement. Now, this is a right triangle that we created here, and so I can also use right triangle trig to arrive at my displacement. And oh snap, will you look at that, I get 2.44 kilometers for my resultant displacement, right on the money. All right. Now, you're also allowed some wiggle room on that answer because you're allowed plus or minus 0.2 centimeters on your measurement, and so you have some wiggle room on your displacement based on the scaling. I believe based on that plus or minus 0.2 centimeters, I have a range of 2.36 to 2.52 based on that plus or minus 0.2 centimeters on the actual measurement. Again, if you're doing this digitally or whatever, if you're not at the right scale, you're going to get the wrong answer. I'm talking about what the official scale was on the actual paper copy of the Regents exam for that year. And they tend to print them on slightly larger paper than 8.5 by 11. I don't understand why, but whatever. 69, using a protractor, determine the angle between east and the hiker's resultant displacement. And they specifically say use a protractor. So the way you would line up your protractor, you would put the 0 mark of your protractor on point P, and you would line up that eastward vector with 0 degrees, and you would see where exactly that resultant hit your protractor. And you should get 35 degrees plus or minus 2 degrees, that it gets anywhere from 33 to 37 degrees. Now keep in mind, if you have 32 degrees or 38 degrees, you are out of luck. It's plus or minus 2 degrees, no more, no less. All right, there's 69. There's your displacement question. Next question. All right, we have ourselves a Jack-in-the-Box. And it says Jack-in-the-Box and a toy. It says 70 through 74, which is maybe obvious. It's only the only question on this page. All right. Jack-in-the-Box is a toy. Figure in an open box is pushed down, compressing a spring. The lid of the box is then closed. When the box is opened, the figure is pushed up by the spring, and it moves. The spring in the toy is compressed 0.07 meters. Ooh, that's data. By a force of 12 newtons. Okay, great. 7071, calculate the spring constant of the spring and show the work. Well, I know the force and the stretch, so I'm going to use Hooke's law for that, Bamajama. All right, so we get, I put in the force, I put in the stretch, I solve for k by dividing the both sides by the stretch. I get 171.428, blah, 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 blah. I really only need two significant figures because the stretch is 2 sig figs, so I round to 170, or more specifically 1.7 times 10 to the 2. And it's newtons over meters because I'm dividing newtons by meters, and so the units for spring constant are newtons over meters. 7273, what's the elastic potential energy? That is spring potential energy stored in the spring when it is compressed. Now that we know the spring constant, we can do this problem. Working the numbers through with, of course, based on the answer to 70 and 71, that 170 newtons per meter is error carried forward. In case you got that wrong in 7071, we would follow that. That's why we're showing work, so we can follow it. But 0.5 times 170 times 0.07 squared is 0.42. And of course, since this is an energy we're talking about here, the units for 0.42 are joules. Do not forget those units. All right, then 74, identify one form of energy to which the elastic potential energy of the spring is converted to when the figure is pushed up by the spring. So what does the Jack-in-the-Box toy do? You have a spring that pushes the toy out, which then comes zooming out of the box. So the spring potential energy becomes kinetic energy, but then eventually that kinetic energy stops and the toy is now out of the box. It's up above the box. And so really, in the end, the kinetic energy becomes gravitational potential energy as you've lifted the toy out of the box. Now, that is not an entirely 100% efficient process. And of course, some of the energy, as always in inefficient realistic processes, goes to heat, which we call Q. So honestly, kinetic energy, you have like kind of three right answers here. You can say kinetic energy because of motion, gravitational potential energy because it's elevated, you're giving it height, and also heat. In these processes, there's always some energy lost to heat. Any one of those, and you don't need to explain it, it just says identify, so you just need to give the answer. And here we are on the last page of the Regents exam from this particular year. I keep meaning to obscure which year this is. I mean, come on, it's kind of obvious that it's 2016, June 2016. So yeah, I don't even know why I'm like blocking it out. I think I'm blocking it out because Miss Coleman blocked it out. She wrote test 1, test 2. It's like, okay. It's June 2016. It's probably obvious by now. And then it's kind of like, oh, I'm gonna look up the answers. These are the answers. So like, anyway. 75 through 80. Let's continue. Let's finish this thing. Yeah. All right. So we have an electricity problem. I'm going to write as we go. So 12-volt battery. I don't really want to use blue. I want to use black. Black. A 12-volt battery causes 0.6 amps. So my current is 0.6 amps. Flows through a circuit. It has a lamp and a resistor connected in parallel. The lamp is operating at 6 watts. So I'll write, what do we have? A lamp and a resistor. So we'll say P1 is 6 watts. And in fact, let's see, 12-volt battery, that's going to be V total. And then our current is 0.6 amps for the entire circuit, so that is the total current as well. So those are the things. Oh, and I'll write parallel circuit so that we know what rules to use. Don't use the incorrect rules for the wrong circuit. 75. Using the circuit symbol shown on the reference tables for physics, draw a diagram of the circuit in a space provided in your answer booklet. It doesn't say anything about any ammeters or voltmeters, so we don't need to include them, but we do have a lamp and a resistor connected to a battery. Now, I don't have the answer booklet, but what I do have is the magic of pinch to zoom. So, there we go. All right, let's draw ourselves a circuit. Battery. Resistor, and connected in parallel with the resistor is a light bulb. Now you can just use the symbol for a resistor. A resistor is a stand-in for anything that doesn't provide voltage. So, and it's not a meter. So a motor, a light bulb, a resistor, and an appliance, anything that is not a meter or a battery, you can use the symbol for a resistor. Now, to be fair, they did provide the special symbol for bulbs specifically, so if they were nice enough to provide the symbol for a bulb, why not use it? So there you go. There's your circuit. Now, one thing that you don't want to do, don't feel like you have to like box it off. Don't be like, okay, there's my box. There's my box is not a thing. In fact, that is a short circuit, and you are going to bypass your resistor and bulb, and you're going to set your battery on fire. So that is not a thing that you want. That is fire, and you just burned down everything. Great job. You do not want that short circuit. That is bad news. There, that's better. Your circuit symbols are on page 4 of your reference tables. Now keep in mind, it does not have to look this way. You could have made your battery kind of going like this way, and you could have done kind of like a vertical orientation situation like that. That would have been okay as well, just as long as the connections are legit. Believe it or not, that was a 1-point question. So I'm not sure. I'd have to check the rating guide, the grading guide, instructions to teachers as to how to grade that thing, because there's a lot going on for 1 point. Anyway, 66, 67, calculate the current through the lamp. Show all work, yada yada. So let's make a table to collect our information as we know it. Parallel circuit, VI and R. We know that the total voltage is 12 volts. We know the total current is 0.6 amps, and we don't know anything. Oh, wait a minute. We know the power, so let's also include. Let's also include a power column, and it says the power of the first, lamp is 6 watts. So we do know the power. We don't know any of the resistances, but we can figure that out. All right. So what they want to know is what is the current through the lamp. Well, now, even though you have a table, when you say show all work, you should include equations. So we know that the total voltage is equal to V1 is equal to V2, which is a parallel rule. So if the total voltage is 12 volts, then we have the individual voltages are also 12 volts. And so now that I know the voltage for the lamp and I know the power for the lamp, P of course is VI, so I'm going to stick in 6 watts for the lamp. I know its voltage is 12 volts, and I'm going to solve for the current. 6 divided by 12, I wind up with half an amp in the lamp. Half an amp in a lamp. There you go. All right, and you should show some work there, so I did show some equations. I did substitute with units, and so there's my answer. Find the current in the resistor. Well, I know that in parallel, current adds up. It's not the same at all points. It adds up. And I know that the current in the lamp is half an amp, and the total current is 0.6 amps, so therefore the current in the resistor must be the difference, 0.1 amps. All right. And then 7980, we want the resistance of the resistor. Now that I know the current in the resistor and I know the voltage across the resistor, that's V over I, 12 divided by 0.1, and I get 120. And the units for resistance are ohms, the Greek letter omega. You can literally write the word ohms if you're not sure. I wouldn't write the letter O, it's going to look like a 0, and it's probably going to get lost with the number, and then you're going to say you didn't put units, and right. It's probably why they use omega instead of the letter O. But there you go, 120 ohms. Of course, we have ECF credit on the 0.5 for 78. That's carryover from 76, 77. And we have ECF from the 0.1 on number over here from number 78. So it is going to be a lot of work trackings for whoever is responsible for grading that sucker. But there you go. Make sure that you use the correct rules for the correct circuit. These is a parallel circuit, so you have to use the parallel circuit rules. Okay, and we're almost done. We have numbers 81 through 85. And of course, it's a modern physics question. And they love in modern physics to trot out some kind of wordy paragraph, etc., that is designed, I think, really to confuse you. And because what you actually need in order to answer these questions is really not that much. But it's currently 10:15 at night, and I am not going to finish this video right now. I'm going to finish it tomorrow, because I have to go to bed. Alright, I will come back to this, and then we'll wrap this video and this Regents exam, June 2016. Good night. Okay, Part C, June 26, Part C, last question, set 81 to 85. Great Nebula in Orion has excited hydrogen gas. The electrons are falling from level 3 to level 2, and it gives a characteristic color. 81 says find the energy in electron volts of the emitted photon when they transition from n equals 3 to n equals 2. So you have to go to page 3 of the reference tables, take a look at the hydrogen chart on the left, and look up levels 3 and 2. Level 3 has an energy of negative 1.51 EVs. Level 2 is negative 3.40 EVs. So my formula is E photon is EI minus EF. Initial is level 3, final is level 2. And so when you work the numbers, paying attention to the negatives, you get positive 1.89 EVs. It's an emitted photon as the electron falls down from 3 to 2, so yeah, it would be positive energy. Now, 82, find the energy in joules, so convert to joules. And so the conversions on page 1 of the reference table is 1 electron volt is 1.6 times 10 to the negative 19 joules. I put the electron volts in the denominator so that I can cancel with the original units, and so I get 1.89 times 1.6 times 10 to the negative 19 joules. So there's the energy in joules. The reason why they want that is because they want the frequency of the photon. We use E equals HF for that, where H is Planck's constant, 6.63 times 10 to the negative 34 joule seconds. That's on page 1 of the reference tables, and we're solving for frequency. So we divide both sides by H, and we get 4.56 times 10 to the 14 hertz. And then for the last question, identify the color of light. So you look at the electromagnetic spectrum on page 2 of the reference tables, and 4.56 times 10 to the 14. And the color is red is because it's between 3.84 and 4.82 times 10 to the 14 hertz. Alright, that was the June 2016 Regents exam. Next up, June 2017 Regents exam.